So historical note. Yes, quickly. Anyone? Okay, we shall divide it into two parts. Okay, one is physics before 1900, physics before 1900, physics after 1900. Okay, because in 1900, Maxwell, not Maxwell. What is that one? That's Planck's what you call explanation for blackbird radiation. It's a kind of breakthrough actually. Okay, so if we see physics before 1900, what you had? So can you quickly quote? So quickly tell me. Classical mechanics. So let me write as CM. Okay, that means Newton's law and its application, isn't it? So so electrodynamics, isn't it? And in that one Maxwell's so EM theory, which is one of the what you call breakthrough in physics. I think 1961 to 62 something. I think. Okay. So thermodynamics. And here optics also. Optics was also there. Okay. Interference, diffraction, geometrical optics, physical optics. Those were very well studied subject. Okay. You can apply this classical mechanics. Yes.
1961 or 1860?
18. Sorry. 1861. So this is, I am talking about physics before 1900, isn't it? Now, classical mechanics, which you can apply to all celestial bodies, and you can explain your solar system and any macroscopic bodies, isn't it? Electrodynamics, it gave very clear-cut idea about charges, current, interaction, so like that, isn't it? Again, so again in 1861 to 62, this Maxwell proposed electromagnetic theory, so which says that what you call a change in magnetic field can produce electric field. Change in electric field can also produce magnetic field, isn't it? That is the Maxwell correction. Changing electric field can also produce magnetic field. That is the correction that is done by Maxwell. That lead to electromagnetic theory, wave theory, isn't it? I think later it is verified by Heinrich Hertz. Am I right? Heinrich spelling. Okay. Later it is verified by Heinrich Hertz. This Maxwell electromagnetic theory. Okay. Now these were the physics before that, and thermodynamics. Thermodynamics was a very old theory, and you have to note down one point about thermodynamics. Thermodynamic is the applicability of thermodynamics is independent of the size of the system. Have you observed that one? Independent of the size of the system. Even if you have some microscopic domain, you can apply thermodynamic law. Are you getting my point? So Einstein told somewhere thermodynamics is such a theory which is independent of the size, which can be applied for the system, which has nothing to do with the size of the system actually. So that's why we are going to apply that thermodynamic rules even in the what you call latest discoveries, just in quantum computation, like that, in that kind of idea. So that's a different part. Again, these were the physics before that one. Okay. Again, in that physics before 1900. Okay. In this physics before 1900, it was very clear that matter, I mean your electron, so proton, neutron, like that, they had only particle nature. What do you mean by particle nature? So we shall have it more interactive. Quickly, what do you mean by particle nature?
Which can interact with other bodies.
Yeah, it can collide other body, like that, and you can measure your position and momentum. You can have the information about position and momentum accurately. Is that okay? If it has a particle nature, is that okay? And one more thing is, it can hit other body. It can transfer its momentum. It can transfer its energy, like that, isn't it? So particle nature, isn't it? So EM radiation, it has a wave nature. Now remember, this came only after that one. Okay, before 1900, this way of thinking was not there. Okay, yeah, wave nature. So I think they never called matter has particle nature. Okay, So that came only after dual nature. Okay. So now EM radiation, which has a wave behavior. I mean light. What is light? That is a electromagnetic wave. That is confirmed here. Okay. So again, now look at here. Apart from this Maxwell EM theory, how do you say light is a wave? Just quickly. So I think before Maxwell theory was also, so there was wave picture of light, isn't it?
From interference.
Yeah, from interference and diffraction, isn't it? So interference, diffraction, and polarization. But again, we usually quote interference and diffraction. Is that okay? Now look at here. Again, even without Maxwell EM theory, you can say light is a wave. Okay, because light undergoes interference and diffraction. At that time, they believed that interference and diffraction can happen only with a wave. Is that okay? So that means a wave in a space at a spatial point, one wave can superimpose with other wave. Okay, so that it can constructively interference, that word, isn't it? It can constructively interfere or it can destructively interfere, isn't it? So that it will give the resultant. But that interference cannot happen with a particle, am I right? At a spatial point, how two particles can interfere and produce more probability or more big particles, that we can't imagine, isn't it? Yes. So interference and diffraction believed to happen only with a wave. Light follows interference and diffraction, but that's why light is a wave. Later in Maxwell electromagnetic theory, it is almost confirmed because again it has an experimental proof also. Okay? Any question here quickly? And one more very astonishing fact of this Maxwell electromagnetic theory is he proved, again I think he has given those equations, am I right? Again dou square E by dou x square is equal to 1 by c square dou square E by dou t square, isn't it? Like that. So very exact similar equation will be followed by magnetic field. Light is an electromagnetic wave. It contains electric field and magnetic field which are perpendicular to each other, which are perpendicular to propagation direction, isn't it? So electric field and magnetic field can coexist in a space. They are not only, again, electric field and magnetic field, they are not only generated by charges and current. Electric field can be generated by time varying magnetic field. Magnetic field can be generated by time varying electric field, so that they can coexist in space and they can propagate and they can carry energy, isn't it? So that was the very important breakthrough in the history. Actually, we understood that one. Maybe electromagnetic wave generated by some source, okay, some charges, current or something. Once it goes to space, it coexists. It is no longer because of charges and current. Is that okay? So that is the very important part that we understood actually. Okay. So before 1900. So now again, at 1900, okay, now we shall see the history. Now look at here, I have one question, okay, I have one question, just note down. Look at here, if you have any challenges, okay, then you will be immersed in study. That's why take these questions, this problem, this assignment, everything is a challenge, okay. So then only you will immerse yourself in a learning. Then you will do more and more. Okay. Now look at here. How do you convince a common person that light is a wave? You can't talk about electromagnetic theory. How do you convince a common person that light is a wave? Okay. So come out with the idea. Okay, because they don't know Maxwell electromagnetic theory. So then how do you convince them? Okay, just work on this one. Now look at here. Historically, during this Hertz experiment itself, he found photoelectric effect phenomenon. I think that's not called as photoelectric effect. He just shared his observation. Okay, when some metal norms, when it is shined by some ultraviolet light, he found some spark. Actually, at that time, I think electron was not discovered. I think electron was discovered. When electron was discovered, I think it is 1897, 96 like that, isn't it?
Alpha particle scattering.
Yeah. So J.J. Thomson experiment, electron discovery. So at that time, electron was not discovered actually. So Henry Kurtz didn't know what is the particle which is coming out. He just observed some spark. Later it is observed. Okay. Photoelectric effect is found in that experiment actually, in the Hertz experiment itself. Okay. So that is discovered by Hertz. Okay. So then in the 1900, what is that one? Planck's theory of black body radiation. BBR means black body radiation, PEE means photoelectric effect. Is that okay? Yeah. Now, so there was one what you call plot which was unexplained. Okay, before 1900. That is, if you have what you call. Okay, I have to first explain about black body. What do you mean by black body? Anyone? So in the next session, let me explain this one very detail. Okay. Any body when which is heated, it will emit radiation. Am I right? If you take a spectrum, wait a second. I'll just get into detail in the next session. Okay, about black body spectrum. Now we shall see if you plot energy density versus frequency. Okay, or intensity versus frequency of any heated body. Let me say any heated body. If it is perfectly black body, it will have highest emissivity actually. Okay. Yes. So it was like this actually. It was this kind of plot, and nobody could be able to explain that one. Okay. So in the next session we shall discuss about this one, black body radiation spectrum. What are the attempts to what you call explain this one? So in case of Planck theory, look at here. Earlier we had matter and radiation. Am I right? Earlier we had no theory which says matter and radiation interaction. Am I right? There was no what you call hypothesis or something. CK. So Planck theory. Okay. So matter and radiation. Again, radiation was well studied, matter was well studied. Okay, earlier. So now in this one, we understood one more thing. Next step, interaction between matter and radiation. In Planck theory, he said that interaction between radiation and matter will happen in a discrete manner. Okay, if you have radiation of frequency nu, okay, if it gives energy to material, okay, matter, it will give only in this order, NH nu. He didn't said light composed of photon. That's the Einstein idea, later idea. Okay, what Planck said was, again, energy exchange between radiation and matter happens in a discrete manner. So that is proposed by Planck. So using that idea, he could able to what you call explain black body radiation spectrum very well. I mean, very 100% explanation of this one. I mean, whatever the formula he give, whatever the formula he derived, using this assumption, that formula will fit this one very well, will fit this graph very well. Earlier there were many attempts by Wiens and relays. Okay, so Wiens approach almost what you call, it was almost close, but it was not used to fit the graph properly. So, but this Planck's idea will fit the graph properly because he will find the formula for this one. Okay, so we shall just derive it in the next session. Wait a second, one second. Now look at here. You have some experimental aspect. Okay, and you are developing some hypothesis, some theory. Okay, so again now look at it. We don't accept Wiens theory. We don't accept Rayleigh's theory. So Rayleigh's theory, isn't it? Why? They don't explain full the graph. Now we accept Planck theory, isn't it? Because that explains graph very well. So then whatever the assumption, that is true. Is that okay? How do you got this assumption? Again, so that's a kind of you can say intuitive assumption, a kind of trial and error, whatever. Okay. Once you do some assumption and you develop the theory, once it explains experimental aspect, okay, then you should believe that one. Now one thing is very clear. Again, energy exchange between radiation and matter, that happens in a discrete manner. If you have a radiation of frequency nu, okay, if a matter receives energy from a radiation of frequency nu, it will receive in the form of n h nu, where n equal to integer. Is that okay? Yes, tell me.
So sir, I mean, what do you think that if I have some assumptions and those assumptions converted into equations,
Hmm.
I mean, how that mind come, I mean, should come.
No, no, actually, this Planck, again, to check out how Planck did all of this, you have to read this textbook, okay? Bose and his Statistics by G. Venkatraman. Can you see this one? Why it is lagging here? Bose and his Statistics by G. Venkatraman, okay? So, he had a kind of flowchart kind of idea. He used to do assumption, he used to work out, he used to try whether it will fit with the theory or not. Then he used to go back and he used to edit the assumption, change the assumption, and he used to work out. By after many trial and error, he got this assumption lead to this what you call very good explanation of this one. Then you should believe that assumption. This assumption is true. Okay. Even though later we found light composed of radiation, light composed of photon. Am I right? Then also look at here. This will be followed, isn't it? This again, if it composed of photon, then definitely exchange will happen in terms of photon. Energy exchange will happen in terms of photon. Definitely this will be followed. But that part is true, isn't it? Look at here. Our understanding of radiation and matter interaction, it is improved in this one. Okay. So next one in again a photoelectric effect which was observed in Hertz experiment in 1905. What is this one? Einstein's explanation of photoelectric effect, which was also not explained, okay, which was not explained so before that one, okay. Now look at here, Einstein assumed, he took one more step further, okay. Einstein, because look at here, at that time it was very well known that light is a wave. How they could think that light composed of particle, even though he said that energy exchange happens in a discrete manner, okay. He couldn't think of it itself composed of particle, radiation itself composed of particle. He couldn't think of that one. But in the explanation of what you call photoelectric effect, Einstein come out with a, I hope so, because of that he got Nobel Prize, isn't it? So now again, he says that if you have radiation of frequency nu, okay, so it composed of photon of energy is equal to h nu. That photon what you call we will have momentum also, that is equal to h nu by c, okay, that is later confirmed by Compton effect. So here we don't need photon momentum concept, okay. So now light composed of a particle, light which was believed to be a wave, okay, it composed of a particle. If you have radiation of frequency nu, so again so it composed of a particle called photon, whose energy is equal to h into nu. If you have a radiation, if you have some energy in the radiation, then the whole, again, that total energy should be integer multiple of h nu. If you have a radiation field of frequency nu, okay, then if you have what you call, if you have total energy of that radiation, it should be what you call integer multiple of so there should be 100 photon, there should be 101 photon, there cannot be 100.5 photon, isn't it? So now this is the discreteness of the light again. So again later we shall, I'll give much more insight towards this one, okay. So towards this what you call so photon idea, okay. Now look at here, it was a kind of hypothesis, am I right? Photon hypothesis, you can say that one, photon idea. Now photon is no longer a kind of hypothetical particle, remember. We have single photon emitter, we have single photon receiver that's been used in quantum communication, secret communication. Is that okay? So that's why again, whatever, again, maybe to fit the experimental aspect or to explain that one, they might have come out with some what you call idea, isn't it? You can say like that, isn't it? So it is not like that, okay. So again, once it explains what you call experimental aspect, as well as once the similar idea can be applied somewhere, so again that will stand actually, that will stand, and that is true, that is the nature. Is that okay? Light composed of photons again if you have a radiation of frequency nu, again it composed of photon of energy h nu. So can you hear me? Any doubt? You can stop me and you can ask the doubt, okay?
So in corpuscular
Hmm.
I mean, somehow it can connect with.
Yeah, corpuscular theory was okay, but again, the problem was he said light travels in a lesser speed in medium like that. There was a lot of problem actually.
Yes.
Yeah, very old one, isn't it? Very old theory, Newton's corpuscular theory.
Yes.
Actually, that Newton corpuscular theory, actually, it misled scientists actually. Over very many decades actually. Later they found it's electromagnetic theory. Now look at here. We have theory to say that how light is acting like a photon, how radiation acting like a photon. We call it as field quantization. Electromagnetic field that is quantized, that one quanta, we call that as a photon. Each quanta, we call it as a photon. Okay, we have a theory for that one. We have clear theory for photon idea, and we have application here. Okay, quickly. Any question? Quickly, you can stop and tell me, ask me any question. Now look at here. Now the what you call challenges. So try to explain photoelectric effect using wave theory. Why photoelectric effect cannot be explained using wave theory? Is that okay? First list out all experimental aspect of photoelectric effect. Okay. So try to explain that one using wave theory. If you can't explain using wave theory, why photoelectric effect cannot be explained using wave theory? Okay. So this is another challenge. So what was challenge one? How to convince a common person light is a wave. Okay. So challenge two. So try to explain photoelectric effect using wave theory, and if you can't explain, why you can't explain that one using wave theory? That's a challenge too. Is that okay? So then, light is a particle or wave. Look at here. Later I will say that light is a particle. Okay. Wait for a while. Okay.
Please repeat the challenge too.
Yes.
Please repeat the challenge too. What do you
Challenge two is okay. I'll just write that one. Okay. Why photoelectric effect cannot be explained using wave theory of light. Okay. Why photoelectric effect cannot be explained using wave theory of light? That is the second challenge. I'll put it into Google Classroom. Okay. I'll create Google Classroom today. There I'll put it as a challenge. Okay. Because again, once you convince yourself why photoelectric effect cannot be explained using wave theory, you'll be definitely convinced that light composed of photons. Is that okay? You should know how hard or how impossible it is to explain that phenomena using wave theory. Then only you will be convinced with that one. Okay. I mean, you know this theory, isn't it? Photoelectric, you have studied in class, but you know this theory very well. But to convince yourself to feel that one, you should first try that one. Is that okay? That's the another challenge. Now later, I think I'll just quote it here. Okay, light. Now again, light composed of photon of energy h nu. Each photon have got energy h nu. They have momentum also h nu by c. Okay. Later in 1923, Compton effect. It verified that one. Compton effect, look at here, it is such a experiment that it's a kind of how you play in carom board. Is that okay? If you play in carom board, look at here, you have a piece here, you have striker here, okay?
So before 1923, I think,
No, photon idea was there. I think this momentum of photon was also defined, but not verified, okay? Now look at here, in photoelectric effect, you can say that to fit the experimental aspect, he might have come out with that idea. Now after Compton effect, you don't question like that. Is that okay? You don't question like that. Look at here, Compton effect is, look at here, again, so experimentally, so you have electron, so you are assuming a photon of energy E is equal to h nu, and so P is equal to h nu by c. It is incident on this one. After incident, it is scattered, okay? It is scattered with an angle theta. So again, suppose this if this is the frequency, if suppose lambda is the wavelength of incident radiation, if lambda dash is the wavelength of scattered radiation whose energy or wavelength, so that depends on this angle. Lambda dash minus lambda is equal to some h by m mass of electron into c into 1 minus cos theta. Okay, this was Compton effect. Look at here carefully. This is such an experiment that, okay, look at here, we can derive, this is the experimentally observed one, okay. This can be derived by assuming photon has a momentum h nu by c, photon has an energy h nu. We are going to apply relativistic energy conservation, relativistic momentum conservation, we can derive this out, okay. Now look at it, it is such an experiment that suppose if you have a big piece here, actually your piece will be small in your carom board, isn't it? So you have a small striker here, okay. You are just shooting your striker towards that piece, okay. So if suppose striker goes here, hits back, you will have one energy. Suppose you are shooting the striker with the same energy, okay. Suppose if it hits back, so back scattered, I'll say like that in this case, okay. You will have some energy, okay. Suppose if it goes like this, if it goes in this direction with some angle theta, okay, with some angle theta, it will have some energy, isn't it? So this scattered striker's energy will change with respect to theta. Can you imagine that one? In case of carom board also, isn't it? Exactly the same thing is happening here. We are going to use what you call collision process. We are going to use what you call momentum conservation and energy conservation, and we will get this one. So this is what we see in the experiment. So that's why it is very clear that light composed of a particle called as photon, so and whose energy code h nu, again whose only energy and momentums are defined. Okay, for a light only energy and momentum are defined. Is that okay? Yes, quickly. Any question? Yeah, again you will understand, okay, whether light is a particle or a wave later.
What is the difference between reflection and scattering?
Reflection. A reflection, look at here again, how you see the phenomenon, that's very important, okay. Again, a reflection can be explained using EM theory itself. Is that okay? EM theory itself. So this is a different phenomena. This Compton effect is a different phenomena. So not all collision of photon with some matter, it will produce what you call so Compton effect, okay. There are some probabilities for this one. We call that as Compton effect cross section, okay. It depends on your frequency also. Is that okay? So there are some probabilities of this event. This event cannot happen for again, if you incident on some metal surface, you can't say that it will happen. Is that okay? So that's a very good question that what he is asking is, what is the difference between scatter? Now here in this scattering, your wavelength is changed, okay. In the reflection, usually wavelength will not change. A phase will be changed, those things can happen, but wavelength will not change actually. Is that okay? Quickly.
So can we say that reflection is a special kind of scattering?
Yeah, you can say like that. You can say like that. Reflection is a type of scattering, but how to say? It's a kind of relay kind, not relay. How to say?
In quantum level, the scattering is same as the classical level.
No, I mean, in any phenomena, we go for our comfortable way of explanation. Is that okay? We can explain that reflection using EM theory very well actually. That we don't need to get into the photon theory. Suppose if you incident yellow light, okay, whatever the reflected one, that will be yellow light. That's a reflection. Okay. Yeah. So, but in this scattering event, whatever this one, again, this can happen only in the X-ray region. Okay. X-ray region. Let me explain this one. Okay. We shall study all of this in detail.
But we can see the scattering, sir. The wavelength will be changed.
Huh.
Whatever we see after scattering.
Wavelength is changed. This is so that's why I think it's called as inelastic scattering something.
But in reflection, the
Again, if you send yellow light again, we we don't use visible light here, okay? In Compton, we use X-rays, okay? But again, your reflection is that kind of phenomena where there is no change of wavelength, okay? If you want to explain the reflection using photon, it is just hitting and it will go back. Or you can say absorption and re-emission also sometimes, okay? So I have to look into that one, how exactly you can explain reflection using photon theory, okay? Photon theory. What we do is in our modern textbook, we go for comfortable way of explanation.
Sir,
Yes, tell me. Yes, quickly.
sir means in reflection wavelength constant.
Incident wavelength is same as reflected wavelength. If incident wave is, again, don't think like incident wave is white light, reflected is yellow light because of the surface, we say surface yellow. Not that concept, okay? I'm saying if you incident yellow light, reflected will be yellow light.
Sir, someone says that. Sir, I have always a problem.
Wait. I got that question. I'll just. Feynman has a video on explaining reflection using photon. Can you share that one, Swapan? Share it to Slack, okay, later into general channel, okay? Yes, that's very good. Again, that's not that straightforward to explain. Again, if photon is reflecting without losing its energy, you should explain why it is not losing energy, isn't it?
Yes.
This event will not happen always. Compton effect will not. Again, if that photon loses energy, that's a Compton effect. That Compton effect you can't observe in the visible region actually, okay? We have some theoretical explanation for that, okay? I have some problems on that one. I think during that, while solving that problem, I'll explain that one, okay? So that question, okay? Yes. Now, he is saying that I always have a problem to grasp how can particle with zero mass has a momentum. Look at here. So this is very good question. You should ask this one and you should clarify this one. Look at here. We say photon has an energy E is equal to h nu. Photon has a momentum h nu by c, isn't it? Look at here. We say rest mass of photon is 0. Okay. So what do you mean by rest mass of photon is 0? That means photon cannot exist at rest. That doesn't mean you can put it in on a weighing box and you can measure its weight. Are you getting my point? That's not possible with photon. They are moving with, again, in a free space, they are moving with the velocity of light, isn't it? C.
Yes.
So that's why rest mass of photon is, again, look at here, concept of mass is never required. You go with a generalized conservation law, everything. You go with momentum and energy. You don't go with mass, isn't it? Are you getting my point? Momentum is the most general term. Mass into velocity, we write like this, isn't it? Mass into velocity, but momentum is the most general term, isn't it? Once you define momentum, once you define energy, you don't need concept of mass at all.
But mass is an intrinsic property of any particle.
Oh yeah, that's true. But again, that's what, again, if that particle has a kind of article, why did you define mass? In the first extent, why did you define mass? Yeah, we can't find any frame where we can. That's also very good comment. We cannot find any frame where photon is at rest. Yes. Now, because of inertia, because of your gravity, like that, isn't it? Gravitational effect like that. That's why you define mass, isn't it?
Yes.
Now look at here. So there is no gravitational interaction actually. So there is no gravitational interaction. That much gravitational interaction. Maybe if you think about black holes or something, you may think of that one. But here again, again, we don't need concept of mass at all in the concept of photon. I think if you read H.C. Verma's book, you will understand that. He has written very clearly. Concept of mass is absent in the photon theory. Is that okay? We say rest mass is 0 because photon cannot exist at rest. What do you mean by rest mass is 0? The meaning is photon cannot exist at rest. If photon exists in free space, it should be moving with velocity of light. Is it clear? Quickly, any question? Can we do elastic? I think your reflection is a elastic scattering. Okay, let me just check out that one. Your reflection is a elastic scattering. Compton effect means inelastic scattering because there is a change of what you call energy of the photon. Is that okay? But energy, again, the relativistic energy and relativistic momentum are conserved here. Okay, yes. Yes,
So
tell.
photon have any charge?
No, photon do not have any charge. Look at here. We don't know what kind of energy this is. I say energy equal to h nu. Now, suppose if you apply your classical concept, whether it is kinetic or potential, isn't it? I'll get to my point. Now, we have to come out of those things actually. We have to come out of those things. So, later in the field theory, we have more better explanation. Photon is a field excitation, they say like that, or field quantization or field excitation. And all of our particles, electron, positron, everything is field excitation. Okay? So, that kind of concept will come actually. So, that's why, so that concept of mass, okay?
So sir, I mean, photon have some definite energy, and if we equate E equal to mc square, how can I equate this?
No, that is done again by de Broglie. E equal to h nu, E equal to mc square. He equated and he found that de Broglie hypothesis derived like that actually. Okay, wait a second. Now he is asking about concept of photon, how to convince yourself it has a zero rest mass. Okay, one thing is that mass concept. You may be thinking that we should define mass everywhere. No, it is not required. Momentum. Once you define momentum, you can use that momentum anywhere.
There is the effect of
No, you don't have to write this one as m into v or m into c something. Is that okay? You don't have to write that like that. Is that okay? Now, you don't write this one as m into c. Is that okay? Because if photon which travels in a, again, this if you write m into c, that is non-relativistic equation again. Photon is a relativistic particle. Is that okay? So this point, very good question. Is that clear? Yes.
Sir, if we can store an extra amount of energy in a small space, can we say that this is a photon, or there is something that defines a photon in a space like that?
No, you have electromagnetic radiation. Okay, in some closed container. Okay, that radiation is quantized. Okay, photon is a quantization of electromagnetic radiation, quantum of electromagnetic energy. You can say like that.
Yes, I can understand. If I say that there is a 700 nanometer wavelength or something of light, and we can say that we can find that frequency or something,
Yeah.
then we can store the extra amount of that energy in a.
No, it's not like storing. It's not like storing. That energy exists in terms of discrete packet.
I think in net.
If you have some electromagnetic energy, that energy exists in terms of photon. You can see, you can have energy transfer, these things, isn't it? Those energy, they are in terms of photon only. And that photon energy, we say equal to h nu, we don't know what type of energy it is. Look at here. We say kinetic energy, potential energy because our classical mechanics expect us to define that one. We will try to define mass because our earlier idea. So again, pushing us to define that one.
Yes.
We don't need that one actually. Is that okay? So one more thing. Suppose if you have energy E1, E2, okay? Suppose E2 minus E1 is equal to h nu. You are incidenting photon of energy h nu. Okay? So we define a process of absorption. Okay? Suppose your atom is in the E1 state. Okay? So again, what it will do is after absorption, atom will go here. Before absorption, you have a photon of energy h nu and atom is in E1 state. After absorption, photon vanished. We say photon is absorbed. Photon energy is taken by the atom. I think this event of absorption may give you some more idea about photon, isn't it? Are you getting my point?
Yes.
It is vanished in this event. If you have electron, you have any event that you have any interaction that it will vanish. Pair production, pair annihilation is different. To have pair annihilation, you should have pair production.
Yes.
a stable electron, it will not vanish, isn't it? So photon is a very different kind of particle. But to work out any dynamics or mechanics part of particle, you need these two, that's sufficient. You can say this is a relativistic momentum, relativistic energy, or energy and momentum, whatever. Is that okay? That is sufficient. Yeah. Concept of mass should not, again, we should not define mass at all. Concept of mass is absent in the photon theory. That's the best explanation. Is that okay? Yes.
So, sir, we cannot apply the normal concept of particle for photon.
No. Normal concept of particle better not to apply, because it is relativistic particle. Our classical mechanics failed in the relativistic domain. Okay, read the first page of Jatili. Okay, classical mechanics failed in the relativistic domain. Classical mechanics failed in the what you call microscopic domain. Remember, so that's why that idea cannot be applied for relativistic particle at all. Is that okay? P equal to me. You can't write that one in case of relativistic particle. Is that okay? Yes. So just see the comment.
Anujanan said that
in photoelectric effect, photon collide with free electron or bound electron. I think there is one problem. Okay, let me upload that problem. I think photoelectric effect cannot happen with a free electron. If it happens, it violates something. I'll give the problem and I'll solve that one. Very good question. Okay, I'll collect all problem today, which will help you to understand that one. Okay, yeah. Why we use maximum kinetic energy in dealing with the photoelectric equation? Because if you again, maximum kinetic energy means that is the energy again your photon energy is converted into energy of the electron. Am I right? Yeah, that again photon is absorbed in case of photoelectric effect, and that energy is taken by the electron. Okay, now that electron may collide with other electron then come out, isn't it? Come out of the surface of the metal, or it may come out without any loss of energy, isn't it? Some electron, after absorption of photon, it may come out of the metal surface. So it may come out of the metal surface without losing much energy. That will have maximum kinetic energy.
yes.
Some electron, again, before coming out to the surface, again they absorb same frequency photon. Is that okay? They absorb the same amount of energy, but while coming out, they may lose some energy. They will have less kinetic energy. So that's why to work out that photoelectric equation, you should deal with the maximum kinetic energy. Is that okay? Because there may be some other event which may lead to loss of energy of the electron after absorption. You can't write the equation for it because that event is very random. That event, it may lose any amount of energy. That's why you can write the equation only for maximum kinetic energy. Is that clear? Quickly. To absorb photon by the electron, photon must be localized. This localization concept will also not existing, okay, later. Localization we say because of classical mechanics, position and momentum, isn't it?
How can you say?
No. Now we have uncertainty principle.
Yes, sir.
Okay, you can't again. You will see that one. Okay, I'll try to explain this one. I'll try to give some idea about uncertainty principle. So again, in case of black body radiation, okay, Bose come out with the idea of dividing phase space into phase cell of the volume h cube, and that idea itself says that even for photon you can't have definite position and momentum.
That's why I think photon statistics developed.
Yeah, photon static developed like that actually.
Yes.
Wait.
Photon go black.
Yes, speak out.
So can you say photon is a localized wave packet?
Wave packet. I think you are thinking a little bit ahead. That wave packet is a concept which came in quantum mechanics, isn't it?
Localized wave packet.
No. Photon is not a concept of localized wave packet. Wave packet means we say particle of different energy. Particle superposition of different energy state that causes wave packet actually. That's a quite different concept, okay? But photon is have got very well defined momentum here. Wave packet concept in quantum mechanics, that is superposition of many momentum states actually of a particle. We deal with particle there, okay? But we say packet, that packet word came because it is a quantization of electromagnetic energy. It's not wave packet concept, okay?
How can you localize, because wave packets means lots of interference of waves.
Yeah, that's what I'm saying. Wave packet concept is superposition of different momentum states. I'll just explain in case of free particle, okay? So, but this photon have got very definite momentum. That's what I'm saying. But still, you can't you can't have localization. Localization means it will violate uncertainty principle.
Yes.
Is that okay? Yes, quickly.
So can I say something?
Yes.
I think it will benefit everyone to understand that the way we understand physics is not through direct examples. We try to develop mathematical models that can best explain certain phenomena in certain conditions.
Yeah, that's true.
So it's not even Dirac in his principles of quantum mechanics enunciates this very properly, that the work of a physicist is not to understand nature in its all explanations.
Yeah, okay. So this is, look at here, we have some experimental phenomena. Okay, to explain it, we develop one mathematical framework. We don't, we don't give any explanation to some of this. We just avoid some question here, isn't it? That's what you are saying.
Exactly.
We just avoid something and we move on, just like mass of the photon.
Yes, sir.
Providing us results with the further experiment.
Yes.
That's all we have to do.
But again, mathematical framework is important, okay? But these are all not mathematical frameworks actually.
Exactly.
These photon hypotheses, these are all not mathematical framework. These are kind of hypotheses actually.
Hypothesis, yes.
De Broglie hypothesis also. Is that okay? Yes. Position uncertainty of photon. Look at here. Once you have definite momentum, it will have what we call infinite position uncertainty actually. Let me try to apply this uncertainty principle to photon. How to apply uncertainty principle? I said photon has a definite momentum, isn't it? Then its position, it can be anywhere, isn't it? Uncertainty definitely exists, okay? Uncertainty definitely exists. In the next session, I will try to explain that one. Energy and momentum simultaneously can't be conserved when photon interact with free electron. Yeah, that is the thing that I'll give the problem, okay? Energy and momentum cannot be conserved when photon interact with a free electron. Photon is absorbed by free electron. That's the concept, okay? I'll quickly write down what are the other part, okay? So after this photoelectric effect, look at here, in 1911, Rutherford theory, isn't it? He said there is a tiny nucleus, again by alpha scattering, okay? Now look at here, so one more challenge, okay? So list out alpha scattering experimental outcome. From that, how he arrived atomic model. Are you getting my point? In case of alpha scattering, alpha particles are shooted towards gold foil. Only 14% of the alpha particles were scattered backside actually. Rest of all were undeviated. Okay? Again, using that fact, so try to explain how he developed atomic model. Is that okay? So then in 1913, Bohr's theory. Is that okay? Bohr theory. That means he says MVR is equal to NH by 2 phi. Using this one, he will derive quantization of energy. He will explain atomic spectra, isn't it? Now look at here. One more question. How Bohr got MVR equal to NH by 2 phi? Another challenge. How Bohr got this idea?
Sir, in left hand side this is a classical one. Right hand side is a Planck's constant.
No, that's why this is not a complete theory. That's what I'm saying. This is not a complete theory. That's why they started developing quantum mechanics at that time. Is that okay?
Can't convince the equation.
No, you can't consider this is not generalized equation also. This one can be applied only to atoms, isn't it? Look at here. Again, in the any other general situation, you can't. Angular momentum is equal to nh by 2 phi. What do you do if there is no angular motion, if there is only one dimensional motion? Isn't it? This is not generalized theory, generalized framework, remember. That's why quantum mechanics developed. Let me explain that one. But my question is, challenge is, how Bohr got this idea? MVR equal to nh by 2 pi. Okay, that's the question. Yes. I think after that Compton scattering, isn't it? So in 1923, so then in 1925, what you call, because of, look at here, these are all not framework, these are all restricted, am I right? Again, even your de Broglie hypothesis, when there is, so 1923, am I right? So de Broglie hypothesis, so again it gave, again, matter, material particle have got wave nature. Wait a second, it is stuck. Material particle have got wave nature. Again, once you say it has a wave nature, look at here, it should have a wavelength that's equal to h by p, isn't it? Material particle means you define momentum well, and associated wavelength will be h by p, isn't it? Later, I think in after a couple of years, 1927, I think it is confirmed by Davis-Germer experiment. Okay, that material particles they have a wave behavior also. Okay, they have a wave behavior also. Later, let me give full explanation of all of this. Okay, we shall study that modern physics point to point, because those ideas are needed. Okay, so that is 1923. But look at here, this idea was also cannot be applied everywhere, isn't it? This idea, again, this may be wave behavior idea, but it cannot. This is again hypothesis. This is a postulate. And this postulate, look at here, this is not giving you a kind of framework, just like Newton's second law. Look at here, Newton's second law was a framework, governing rule, which we apply everywhere. Am I right? In case of electrodynamics also, once you find the force, if that is force, either it may be electromagnetic force. Again, you write F equal to m into a, isn't it, or F equal to dp by dt, isn't it? So that is a framework, but again that can be applied anywhere, isn't it? So, but these are not frameworks, okay? So these are what we call restricted actually. So that's why. So later, in 1925, Heisenberg started matrix mechanics to explain some spectra. Okay. Later in 1926, Schrödinger proposed Schrödinger equation, wave mechanics, and again in 1927 Born proposed probabilistic interpretation, and later Dirac, he just we can even show Schrödinger approach and Heisenberg approach which are equivalent. Later Dirac gave the most general formalism in the abstract notation, Dirac formalism, Dirac bracket algebra, like that. So not only that, so in 1928, okay, look at here, 1925, Heisenberg. What is the spelling? Whatever, okay. Heisenberg, 1926, Schrödinger, okay. And in 1927, Born probabilistic interpretation, okay.
Yes, Max Born.
Born probabilistic interpretation. I think H should be there somewhere, okay. And in 1928, again Dirac made one more breakthrough, that he gave relativistic approach to quantum mechanics. He gave relativistic Hamiltonian. We call it a famous Dirac Hamiltonian. So he predicted what you call pair production, and antiparticle concept, pair production. Later, after 4 years, that is found in lab. He said a material particle behaves like a wave, isn't it? After a couple of years, 1923, I think in 1927, it is found in lab. In case of what is that experiment? Davis-Germer, isn't it? Yeah. So similarly, so these things happened in the history, isn't it? I mean, they propose something, later after some time, so it will be verified, isn't it? Again, if I quote, laser is that kind of theory. First theory is developed, then it is realized in the lab actually. Okay, so these are the history, brief history. Again, you can go through that one. First 3 pages, he has given very nice history. Just go through that one. If you have any doubt, you can ask me. I'm also curious to read some more part of this one, because modern textbook will give, how to say, modern approach. Again, we are losing some historical approach actually in our modern textbook. So that's why I'm also curious and I'll try to find the answer. Okay, uncertainty to photon. Actually, I thought of this one. Okay, I was thinking about photon and uncertainty for very long time, and I couldn't get better explanation. Okay, is it possible to find wavelength of some spectral line very accurately? Is it possible? No. You have energy time uncertainty actually. Are you getting my point?
Yes.
Breadth of the spectral line,
Yes.
natural breadth actually, natural broadening.
Broadening.
I think that itself says that you can't have a spectral line which is very exact, which has only one wavelength without any uncertainty.
Even monochromatic lights.
We say monochromatic. How much monochromatic it is, isn't it? Yeah, this is what I was thinking a very long time ago. How much monochromatic we can make the light, a given light. Is that okay? I mean, how much well defined that momentum of a photon, isn't it? You can't make 100% monochromatic. There comes your wave packet concept. If it is a superposition of different momentum state, wave packet concept will come, but that is not quantization concept. Okay, wave packet concept is different, quantization concept is different. Okay, quantization of electromagnetic wave, that's called as photon. Okay, before quantum mechanics we define photon momentum accurately. Okay, try to what you call separate those aspects. Okay, that's very good. Bohr didn't talk about, I think, but we say this is one of the postulate of Bohr theory. Okay, I too don't know the history properly. Just check that out. He's saying that Bohr didn't talk about quantization. Actually, again, how this came. Just try to explain that one. Okay, how this assumption came. Remember, not because of wave theory of the particle. You may think that again particle behaves like a wave in an orbit. It should be sustained pattern. Because this is 1913, this is 1923. Wave behavior of electron that is found later, remember. This is 1913.
In between 13 and 23, I mean, some postulates are there maybe.
No, but again, how he got that one at that time, how he come out with that one. Just try to find that one. It is not any logical explanation, okay? It may be some historical explanation. There are some what you call input for this one actually. Then he made it as a set of postulate to derive the energy like that. Okay. So again he's commenting something. Yeah. Energy and time. There exists uncertainty also. We shall see that one. Okay. Yeah. Quickly we shall close this session, and I'll not touch this historical part again. We can discuss in Slack. Okay. This historical part, because not much important for our syllabus, but we shall start with black body radiation. I'll come online. What shall I do? If I come online, I think I can't finish in time.
Shivangshu said, Sir, somewhere I have heard Bohr didn't talk about quantization of angular momentum. He written something else in his paper. Like Schrodinger.
That is the problem with a modern text. We don't study historical part. We study in a more comfortable way actually. Ultimately, but our understanding is important. It doesn't matter how that understanding came in the history.
Yes, sir.
But right now how we understand, that is important actually. Okay. Later you don't worry about that one. Okay. You will not be worried with that one. Only in the beginning part of quantum mechanics you may be worried about that one. How this came and all. Okay. But I want logical explanation for photoelectric effect question. I want logical explanation for light behavior, okay, as a wave, okay. But this may be some historical one. It's not because of wave behavior. You can't again using wave is using this one. You can derive this one. But that is not what I am asking. Okay, so try to find some history. Yes.
Sir, could it be possible that he came up with MVR is equals to NH1 through Rydberg's formula? I mean, it does talks about the spectral lines in terms of N that is.
No. How it came? What did you said? I didn't get. Wait a second.
Rydberg's formula.
Yeah, exactly. There was a ridge combination principle. They studied spectral lines so well, they try to connect that wavelength to some integers.
Yeah,
I think he might have worked back
worked by that. Exactly, yeah.
and found some postulate. And again, using this one, later we can have quantization rule. We call it as old quantum theory, Bohr-Sommerfeld quantization rule. Okay, we define one integral in a phase space, so that's equal to what you call n into Planck constant.
But that will be relativistic, right?
Huh?
Relativistic.
No, not relativistic. We studied the same thing in case of WKB method. WKB method is also old quantum theory. There is a old quantum theory. He mentioned that one. Okay, in the first chapter, Bohr-Sommerfeld quantization rule. Some integral of p dq,
Yes.
closed integral of p dq, that's equal to n into h. So that will give energy quantization actually. That Bohr-Sommerfeld quantization is not bad. That's also kind of governing rule actually. Better, because that Bohr-Sommerfeld quantization you can apply anywhere, isn't it? So canonically conjugate variable. Suppose if you have suppose p and q are canonically conjugate variable. Is that okay? So closed integral of p dq is equal to, I think, n into h. So if it is linear momentum, it will be what you call, if it is px, it will be x. Okay, if it is j, it will be pi. So, or if it is Lz, it will be pi, like that. Canonically conjugate. I mean, the concept comes in classical mechanics. Okay, so px, x are canonically conjugate. Py, y, pz, z, Lz and pi. These are canonically conjugate. So this is actually a little bit generalized, what you call, concept
So what
actually.
is canonically conjugate?
Again, that concept came from classical mechanics. Okay, canonical, the word mean, I think, the very basic kind of thing. I think the word which came from canonically conjugate. I'll tell you. Okay, that is defined like this. This momentum is equal to dou L by anyone dou Q dot. So this, whenever this relation is true, we say these two are canonically conjugate. This whole quantum theory, this came after this Lagrangian and Hamiltonian mechanics. Okay, that's why some part of Hamiltonian and Lagrangian mechanics, that concept exists here. Yes. No, not minus sign. You are thinking about what you call Hamilton's equation. Hamilton's equation is different. There is no minus sign here. Okay, you are thinking about Hamilton's equation. Yeah, that's correct. This whole thing which came from classical mechanics only. Obviously, they could think of that one only, isn't it, at that time? But quantum mechanics is quite heavy deviation. These things, this small thing, it had what you call link with what you call classical. Look at here. You said why MVR equal to again how he connected to what you call MVR, which is angular momentum, which is a classical concept, isn't it? They were trying to explain using they were trying to relate that to some classical thing only. So that's why again this action integral, not action integral.
Action is different.
Action integral is integral of L dt, and maybe action variable. Okay, it comes in Hamilton-Jacobi theory.
Yes, sir, it is action variable.
Action variable. Okay, yes. Yeah, again we call it as J. I don't use word J, okay, because sometimes J we use for angular momentum. Okay, so that's why. But in Hamilton-Jacobi theory, this is defined as J. Is that okay? Yes. Now again, they were trying to give a framework using obviously classical mechanics only. So this is one of the attempt, and the very similar thing will come at the end of our quantum mechanics, WKB method. Okay, so a kind of approximation method. That's also old quantum theory. Is that okay? Yes, again some classical mechanics link is there, but we can manage. Okay, we can learn these things later. This classical mechanics, Lagrangian and Hamilton, we can learn later. Okay, because here we use Hamiltonian, Hamiltonian means total energy here because we are talking about conservative system. That's why again we can somehow manage without Hamiltonian mechanics and Lagrangian mechanics. Is that okay? We may use some word canonically conjugate like that. You will get exact idea in classical mechanics. Okay, this is defined like this. Canonically conjugate variables are defined like this. We write Pj Qj. That can be if suppose this is angle, this will be angular momentum. If Qj is angle, this will be angular momentum. If Qj is linear, some x, y, z, so this will be correspondingly px, py, pz like that. Okay, like that it will come. Yes.